We will do today a principle known as Harnack's principle. Harnack's principle for harmonic functions. We require an inequality to do this, and that inequality is also known by the same name, that is Harnack's inequality. Uh, it states that if I'm stating this Harnack's inequality for unit disk, for an arbitrary disk, it will be just a corollary to this. And it states that if we have u be a harmonic function, on unit disk T, and we suppose that it is continuous on the closure of the unit disk. Now, if on the boundary of the closed disk it is non-negative for all theta, then for any point in the disk, I'm taking in this polar form, for any point in the unit disk T, the following inequality holds: 1 minus r, 1 plus r, multiplying it with 0 will be less than or equal to value of u at point z. This is less than or equal to u of 0 times 1 plus r upon 1 minus r, and note that clearly we are taking z in the unit disk, so r is less than 1, and further this estimate is sharp. That means this equality can be attained for certain functions, and the function for which this equality uh, is attainable, I'm giving just this example, you will have to verify it, and the function is for which this estimate is sharp is uz is equal to real part of 1 plus z, which is a harmonic function, obviously 1 minus z, and the equality holds in Harnack's inequality at and z equals to plus minus r. Okay, you might see, you just apply the Harnack's inequality and substitute this value r and minus r. You will see the equality holds throughout in this inequality. So let's move on to work out the proof of this inequality. And for the proof of this inequality, we actually first require an important inequality of the Poisson kernel. Remember, we have this expression for Poisson kernel. PR theta is given by 1 minus r square when r is a number less than 1. 1 minus 2r cos theta minus t plus r square. So what is instead of taking it, I'm taking theta minus t. Let it be only theta first. Let it be only theta. Okay. You know now we know this thing that, and the cos function has this inequality. It takes the maximum value 1 and minimum minus 1. So let us multiply. And if I multiply throughout this inequality by minus 1, still the inequality will remain same. I will have this minus 1 less than or equal to minus cos of theta will be less than or equal to 1. Again, the same inequality will remain. Let's multiply it with 2r, r being a positive number. R being a positive number, so the order of the inequality will not change. You will have minus 2r less than or equal to minus 2r cos theta is less than or equal to 2r. Now let us add 1 to throughout this inequality, because adding a number to the inequality of real numbers doesn't change the inequality. So it will be 1 minus, and indeed I'm adding 1 plus r square. So positive number, even if it would have been a negative number, the inequality wouldn't have changed. 2r is less than or equal to 1 plus r square minus 2r cos theta. This is less than or equal to 1 plus r square plus 2r. Now let's look at the bounds of this function 1 plus r square minus 2r cos theta, and see this thing, the left hand and number, that is 1 plus r square minus 2r is 1 minus r whole square, is less than or equal to this number 1 plus r square minus 2r cos theta is less than or equal to, on the right hand side, what do we have? We have 1 plus r whole square, and if we take the reciprocal throughout the inequality, we will have this reciprocal of 1 plus r whole square will be shifted to the left hand side, and the reciprocal of 1 minus r whole square will go to the right side. So we have, taking the reciprocal, we will have 1 upon 1 plus r square minus 2r cos theta will be less than or equal to 1 minus 1 upon 1 minus r whole square, and this is less than or equal to 1 upon 1 plus r square. And let us again multiply this inequality throughout by some another positive number. And now the positive number that I'm going to take the positive number 1 minus r square, which is a positive because r is less than 1. So multiplying with 1 minus r square, I will get 1 minus r square upon 1 plus r whole square is less than or equal to 1 minus r square 1 plus r square minus 2r cos theta is less than or equal to 1 minus r square upon 1 minus r whole square. Okay, so the middle part is what? This middle part is the Poisson kernel pr theta, and on the left and right side you might make some simplification further. 1 minus r square, you might use 1 minus r into 1 plus r, and you will be left with 1 plus r, and because 1 minus the term of the denominator will cancel out with 1 minus r, and you will be having in denominator only 1 minus r, and similarly on the right hand side you will be left with 1 minus r upon 1 plus r. So this is the inequality that is required for us to prove this Harnack's inequality. So you might prove it as a separate or as a part of the proof of this theorem. And so now I'm just using theta minus t instead of theta. So what I'm going to do, I'm having z, let us take z to be reit instead of theta. Let's take z to be reit, and let us take z to be reit and be a point in the unit disk, and use the inequality. I'm taking, instead of theta, I'm taking theta minus t now, using the inequality 1 minus r upon 1 plus r is less than or equal to pr theta minus t 1 plus r upon 1 minus r. So let's multiply this inequality by some number. What I'm going to do, multiply it by this number u value at ei theta upon 2 pi. I'm multiplying it with this number, and since multiplication by this number to this inequality will not change the order of the inequality, why it will not change? Because you, by hypothesis, on the boundary the function is non-negative, and multiplication by a non-negative number doesn't change the order of the inequality. Multiply with this and then integrate with respect to theta. From we will integrate it from 0 to 2 pi. We get, now what you are going to get, you are multiplying it with 1 minus r, you are multiplying it with u e I theta, and then you are integrating. I'm taking 1 minus r, 1 plus r outside because it's a constant thing. 2 pi, then your d theta upon 2 pi. And again, integration will not change because you are integrating positive function or negative functions. And the middle part, we will have integral from 0 to 2 pi. It will be u e I theta pr theta minus t d theta upon 2 pi, and the right hand side will be again 1 plus r being constant, 1 minus r. It will be integral 0 to 2 pi. It is u e I theta d theta upon 2 pi. So look at this inequality, what it gives you. You have the function which is harmonic, and harmonic functions have the mean value property. So from mean value property, this is, what is this? This is the average of the function on the circle of radius 1, and by mean value property, this has to be equal to the value of the function at the center of the circle, and at the center of the circle means this has to be equal to value of the function at 0. And similarly, at the right hand side of this inequality, it is u at 0. And so we have this inequality now. Thus, by mean value property of the harmonic functions, mean value property of the harmonic functions, what do we have now? 1 minus r upon 1 plus r, value of u at 0 is less than or equal to integral 0 to 2 pi. This is u e I theta pr theta minus t d theta is less than or equal to 1 plus r upon 1 minus r u at 0. So the middle part is nothing but is the Poisson integral of u, and thus by Poisson integral formula, by Poisson integral formula, and this thing 0 to 2 pi u e I theta, it has to 2 pi भी है यहाँ पर, u I theta Poisson kernel pr theta minus t d theta upon 2 pi is nothing but it is the value of the u at REIT. That is REIT is the z. Hence, we have this thing, and substituting this value there in the inequality here in star, I have this 1 minus r, 1 plus r, u at 0 less than or equal to u at z, and z is REIT, so t is a dummy variable. You may replace it with REI theta as I has used this term theta in the beginning. So it is uz less than or equal to 1 plus r upon 1 minus r u of 0. So this is all about Harnack's inequality. The same process can be applied. The same kind of inequality can be derived for Poisson kernel when you have arbitrary disk instead of the unit disk, and you may write that there is another process if you want to rescale What is the rescaling? Let me first state the corollary, then I will tell you how you will rescale or what you do. Corollary is that if u is a harmonic function on an arbitrary disk with center A and radius r, and is continuous on the whole of the disk, for the closed disk, continuous on the closed disk TAR, such that on the boundary the function is non-negative, such that A plus R ei theta, this is the boundary point of this disk, this is non-negative, then we have this inequality for any z equals to A plus R e I theta in the disk for any point here. We'll have this inequality R minus R upon R plus R. Now value of u at the center, u at A, is less than equal to value of u at Z. This will be less than equal to R plus R upon R minus R and u of A. For any, since we are taking Z in the unit disk DAR, and clearly R small r is a number which is less than capital R and it's greater than or equal to 0. So this is the Harnack inequality for general disk, and the proof can be done by either by just follow the proof of the Harnack inequality for unit disk. You just take arbitrary disk, you just take the expression for Python kernel for arbitrary disk, and you just try the inequality, and you just again use the mean value property and the Python integral formula. Or there is a way what you do, if you have arbitrary disk, this is an arbitrary disk of radius A, sorry, center A and radius R, and what you want to do, you want to map this disk onto the unit disk. So what is the process? What you can do, you just define a map. You just map zeta from this disk onto zeta minus A upon R. Now notice that you check the modulus of this new number, zeta minus A upon R. This is a map. This is a map from this disk DAR onto this disk unit disk DAR, and this map is nothing but just it is a conformal mapping indeed. It is bijection. It is a conformal mapping. You may consider it is a conformal mapping. So and what do you have? You have a harmonic function defined on D. It's a real valued harmonic function defined on D. So since this function that I defined on this from this disk with center A and radius R to the unit disk, it is a conformal mapping. It has its inverse. You just evaluate its inverse. That's an easy thing. You just evaluate its inverse. Let that inverse be denoted by something T. So then you compose this function U and T, you get a function, you will get a harmonic function. You will get a harmonic function from unit disk to, and this harmonic function from unit disk is T followed by U. This is now defined on unit disk. So this is the harmonic function, and again you have to check out that on the boundary of the unit disk, it will satisfy the conditions that are required for the Harnack inequality for the unit disk. You just apply the Harnack inequality on this new harmonic function, and then what you change, you just again change the, once you have the inequality, you again change the variables back to this disk this disk center A and R, then you will get the Harnack inequality. So one of the ways to do this thing, if you are comfortable at changing the variables, And if you're not comfortable in changing the variable, you just follow the proof and try to see whether it exactly replicates the things or it has some modification. Okay, any question? So, no question? Okay then. So, now let's come to the Harnack's principle. But before Harnack's principle, let me remind you one of the results. Briefly, I'm going to uh, recall that thing because that is the thing that we will be using. Is that uniform limit of harmonic functions? Harmonic functions is a harmonic function. This is something that we have done. Okay, we will be using this result in the proof of the Harnack's principle. That is, Harnack's principle is also known as Harnack's theorem also. So let us state the Harnack's principle now. Let Harnack's theorem or Harnack's principle is regarding the sequence of harmonic functions. So it has a beautiful conclusion for a sequence of increasing sequence or a monotone sequence of harmonic functions. And let us take un be an increasing sequence of harmonic functions defined on a domain D. Then, so you have the simple hypothesis that it's the increasing sequence of harmonic functions, and based on this, you don't have any other extra condition. They're just the increasing